So we are going to read another paper, BLIP-2, by, as you notice, more or less the same group of people from Salesforce. This paper is interesting. If you recall, the BLIP-1 architecture had 4 columns, isn't it? There was the image encoder column. There was the text encoder column, the standard BERT-like column. But then there was this, well, in reality, even though it was, then there was a column for text, which was image grounded with the cross attention. And then there was a decoder column, right? Now, the in between 2 columns, the second column, text encoder and the image grounded text encoder, the only difference is in one pass, you switch off the cross encoder, begins to behave like normal BERT. In the other pillar, you enable the cross encoder. Yeah, cross attention. Sorry, yeah, cross attention. And then you get an image grounded response. That's the only thing. You, in reality, share weights, like they are the same thing. In this paper, they actually simplified it. And much has happened. If you look at the dates of this paper, it came out towards the end of 22, I think the first version, but the later it was revised. What this paper says actually is something quite remarkable. It says that, see guys, image encoders have matured. VITs and the clips, they have become quite mature, isn't it? So how about this? We take off-the-shelf image encoder and you don't touch it. Just use it in inference mode. If you use it in inference mode, then their weights are frozen, isn't it? You're not touching their weights and biases. Parameters are frozen. And for decoder, forget about training your own decoder. Why? Because these LLMs do such an amazing job at the generation task, isn't it? You can take any large language model and just take it out of the box. Don't touch it. Take LLaMA, take whatever you want. And that's the main message here. It says that, let's do this. Pick one off the shelf. Pick a large language model off the shelf. All you need is that the text somehow has to be image grounded and be fed into the decoder. Because if you really think from a pure LLM perspective, you give it prompt and output comes out, generation comes out. The only thing that we need to do is give it image grounded text encoding, isn't it? And so how do we produce that image grounded text encoding? That is, just put a little network in between, right? So, you know, it's like between 2 giants, like 2 buildings, you make a tiny bridge. One big tower does your image encoding. Another big tower does your decoder, is your large language model. But you put a tiny little network, glue network in between, which they call the Q form, query transform. What does it transform? Your query is given your input. And what it does is, it also has some extra vectors that it feeds in, but that's mechanical, the internal part of it. One of the things people realize is that along with the text, if you also feed in some learnable queries, like some vectors that the machine learns in addition to the text that you feed in, it just gives better results. But for the time being, just ignore the queries. Then with proper image grounding of that text encoding, whatever comes out, pass that into the decoder, right? Then the advantage is, look at this. This is frozen. This is frozen. You just bring 2 off-the-shelf models. You have to only train the Q form in between. Do you see that, guys? Right. And so it represented a significant simplification. It is doing exactly the same thing as BLIP, except that it is outsourcing some of the task. Right. It is delegating the decoding to a large language model, and it's saying, let's take the off-the-shelf encoder. So the whole question is, does it work? Right?
Is this something like this? Actually, I think take a prompt and give it to the LLM.
There is an analogy here, Guru. You said, is there a resonance of something like this to RAG? See, in RAG, you do that. Given a query, you go and get search results and you ground your query with the search results in RAG. And then you give it the whole thing to LLM. Very similar to that. You take the text, ground it with the image encoding, and then you apply cross attention. In this case, not the text, but the overall, the encoding that comes out of that, right? Image thing, that you pass on to the LLM. So, exactly. That is it. That is it. Encoding. Exactly. So there is a similarity. Yeah. So now let's read this paper, and you will find that the paper is short. I won't hold you for too long. Let's read this. The cost of vision and language pre-training has become increasingly prohibitive due to end-to-end training of large-scale models. This paper proposes BLIP-2, a generic and efficient pre-training strategy. And the word to pay attention to is a generic and efficient pre-training strategy that bootstraps vision language pre-training from off-the-shelf frozen pre-training image encoders and frozen decoders. Frozen means you just download it, don't do anything to it. Right? A BLIP-2 bridges the modality gap with a lightweight query transform. Is the new word they cook up, querying transformer, which is pre-trained in 2 stages. The first stage, bootstrap vision language representation learning from the image encoder. So the image encoder will produce something. The second stage bootstraps vision to language generative learning from a frozen language model. This, again, the picture says it all. Right? BLIP-2 achieves state-of-the-art performance on various vision language tasks despite having significantly fewer trainable parameters than existing methods. For example, our model outperforms Flamingo ATB. By the way, we'll cover the Flamingo paper also. Flamingo is an important paper. It says that it outperforms Flamingo by 8.7% on zero-shot visual question answer tasks. And this is the important thing. So it beats Flamingo, which was a state-of-the-art model at the time, with the 54x fewer trainable parameters. Flamingo was ginormous. Imagine 2% of it. Something that's just 2% size of it. We also demonstrate the model's emerging capabilities of zero-shot image-to-text generation that can follow natural language instructions. So basically that. Now, how does this work? Let's do that. So I'll ignore some of the basic things. Visual language sits at the intersection between vision and language. Therefore, it's naturally expected that vision language models can harvest from the readily available unimodal models from vision and natural language communities. In this paper, we propose a generic, compute-efficient VLP method by bootstrapping from off-the-shelf models. Right? I'll ignore most of it because the ideas are very clear. Now let's literally look at this, how this works. First part, model architecture for the Q-former. What do? You take an image encoder and some learnable query parameters. Just think of query, the learnable queries are just think of vectors that also have to be learned during training through backpropagation, nothing special. What do? You take, and now let's pay attention to this. Remember, this is cross attention. Do you see the cross attention there? Why do we need the cross attention? Image grounding. That's right. Image grounding. And so do you see your familiar image text matching? The only thing, so you still are doing the IT contrastive loss, right? Image and so this is image text matching, image text contrastive loss. Both of those are there, right? Where did the image text matching is one loss and image text contrastive learning is also taking place. Now, you give it an input text to this, it will produce self-attention, feed forward. Now, you realize that this is producing image-grounded text generation, right? And all of this looks familiar, right, internally. Right? It's the same thing. The most important thing is that you are just using cross-attention between these two. There's nothing actually after the previous paper, you'll find it to be fairly straightforward to learn. And we can just learn from, instead of reading the whole paper in detail, we can learn from the pictures itself. So let's look at pictures here.
Learn queries in the previous. What is the example of this in the previous diagram?
Oh, learn quiz are just vector. Don't pay too much. They use the word learn quiz because it's in this literature. People, what they have found is, see, your text will become embedding vectors, input vectors, input embedding vectors. Each of the token becomes that. What they are saying is, along with that, have a little arsenal of extra embedding vectors that in some sense you prepend to this text. So remember,
example, if you take the previous example, the quick chat something like that.
So let's take an example.
Yeah,
see, you would do the cow jumped over the moon, right?
Yeah.
So remember that you used to use CLS token. What they are saying is don't do CLS token. So what happens is put a CLS and go forward with it. So one of the things that people learned is, see, this becomes a vector, E, cow, J. So they all become input vectors, embedding vectors. So what you do is don't make CLS also into a vector. Instead, have some pre-cooked vectors. Let's say 5 vectors. They're just hardwired, right?
Standard.
Just standard vectors, a library of standard vectors.
They're unique. For that model, you decide and keep it.
Yeah. They're just frozen into the model. Now the whole question is, okay, then what directions do those vectors point to? The answer is very simple. Hey, through backpropagation, figure out if I have to have 5 vectors that I'll pass on along with the text embeddings, what should be those 5? What those 5 vectors should be? Right. That's why they are called learnable. Learnable queries means learnable vectors. That's all.
They finally settle on the learned one, the 5?
Yeah. So through backpropagation, they will figure out what those vectors are. No, see, I'll put it this way. See, the cow jumped over the moon. The text will keep changing.
Yeah.
But for some, they find, and at this moment, in a simplified way, that if you not only send those vectors, input vectors, but if you also wrap them up with some extra vectors, fixed vectors, forever fixed. And then what happens is, in a fully trained model, they're forever fixed. So then what happens is you get better results. Generally, they have found that these are called learnable vectors.
And those during the training phase, they go to that property.
Exactly. Now the whole question comes that, hey, that is all fine. And how did you even have the idea of prepending them with this extra vectors, sending these extra vectors? And the answer to that is, hey, people keep hacking. And somebody must have noticed that the concept of learnable vectors, right, extra vectors, then the question comes, those vectors, each of the vector is ultimately nothing but some numbers, right? Suppose it's a 10-dimensional vector. I'm giving an example. In reality, these are high dimension, 300 dimension, 500 dimension, whatever. So it is ultimately made up of floating point 1. These are floating point numbers, right? How do you know their values? I mean, that measures which direction the vector points to. And the answer to that is, hey, just let it pick it up from backpropagation. In which direction should we point these vectors so that at the end of the day, the machine learns well. What is the real intuition? I will hazard a guess. I'm not absolutely sure. My hazarded guess, and I've seen this in many situations, it is as though these vectors, right, they form, like, for example, when you're traveling, would you not like to have a compass with a north-south? Isn't it? One pointing north, one pointing south, etc., right? And one pointing up, so that as you walk around, you have a sense of where you are, which way you're heading. And to me, these vectors that I have seen in many situations, many research papers that are learned vectors, to me is almost like learning a compass to guide the input to sort of orient itself. That's the intuition I carry with me.
They are doing image grounded text, right? And these query vectors are the ones that is grounded.
In some, no. That is different. The grounding is coming from this. You see this line, right? Cross attention. this query is learned queries, right? What you are basically saying is, let us give the learned queries for cross attention. You see here with the image. Okay, in the standard blip, the old blip, let me go here and see. Let's go to blip. Yeah, I'll blow up this image. You notice that, look at the second pillar. What are you giving it? You're giving it the actual input, right? But in the new architecture, they're saying don't give it the actual input. Only give it some fixed, almost like give it a fixed sentence. What that sentence should be or what those are learned queries. That's it. Forever hardwired. Now the only question is, what is that? So what happens is that this link is broken. This link is broken. You see this link, right? This is broken and it is replaced with some learned vectors. That's it. They're saying, don't do this. Don't send it to both the pillars. Just send a fixed one to this. Actually, is the third one. Yeah, third one. To the third one. Third one. See, is the cross attention. Yeah, you're right. Actually, is the other way around. This one, don't send this one here. Instead, send some in the cross attention. Just send this. So the architecture slightly changes. And they must have, see, a lot of these things are learned by playing around. So you notice the text goes in and it creates your standard text vector, BERT embedding, which goes through contrastive, right? But image text contrastive learning, it will go through. But this one, in where the cross attention is happening, the pillar in which cross attention is happening, just put the queried vector. Yeah. So compared to the original paper, they have reversed the two pillars in this. That's all. That's the internal detail. But the main message of this paper is the inner two pillars are more or less the same with minor change. In one, you just feed it, instead of the text, you feed it some learned vectors. Right? Think of it as a learned hardwired sentence or something like that, which becomes vectors. And then you do this. So let's look at that. BLIP second stage, vision to language generative retrieval. So first stage is what? Modal architecture of Q-former, and BLIP's first stage, language representation learning objective. We jointly optimized three objectives which influence. What were the three objectives? We are already familiar with. Image text matching, right? Then contrastive learning, the clip kind of a thing. And then you have image grounded text. These are the three loss functions from the previous paper, right? Exactly the same. And then what do? You go to the second phase. What do you do in the second phase? In the second stage, vision to pre-training, which bootstraps from frozen language and LLM, bottom, bootstrap and encoder decoder based LLM, right? So there will be one problem there. Your Q-former is going to produce a vector. Let's say that here, think about this way. A Q-former may produce a vector, the ultimate vector, which is a text, image grounded text and all of that nice things, right? But there is a problem. Based on which LLM you use, they all expect inputs of a different size, right? So one LLM may expect your queries, your tokens to be of size blah. It may take so many tokens and each token dimension is something else, right? So how do you align the two? Obviously, you will do what? The simplest rule is you will multiply it by a matrix that will change the dimensionality of it. Right? So if you have a three-dimensional matrix, you want to make a three-dimensional vector, you want to make a two-dimensional vector, how would you do it? You'd multiply it by 3x2 matrix. Yeah. But when you do that, you also have the opportunity to bring in some more deformations. Why not throw in some fully connected layers? Because it will learn something. It will learn the best proper glue to do that, which is what they do. In the second paper, if you notice, the second stage, all they do is they introduce the output of the Q-former. They just feed it into a fully connected network that will align the output of the fully connected network will be aligned to what the LLM is expecting. Does that make sense? That's all. I mean, no magic here. Right? There is nothing very shocking here. Now, what happens is when people use a decoder, you could use a decoder-only model like GPT, or you could be using an encoder-decoder. Sometimes what happens is people put a full transformer like Flan T5 or something like that, T5 or something. Doesn't matter. All you have to do is whatever the input of the, whatever you downloaded, model that you downloaded, if it is a decoder only, it's an encoder decoder, you just need to know what the input is, what the shape of it is, and align the shape and you're done, right? That is that. You do some alignment, and then the prefix while training it, you give it the cat wearing. For example, if you give it just a decoder model and you give it a picture, then your loss function, you will train it on a cat wearing sunglasses should be produced. If you give it an encoder decoder model, then you can be smarter. You could say a cat, and then you expect wearing sunglasses to come out. Yeah. So that's all there is to it. That makes it into the BLIP-2. BLIP-2 was very successful. Let us see how successful it was. So guys, do we get it? It is nothing but your blip, right? Except that some parts you have just borrowed, downloaded and borrowed. You don't train. And these models, how big are these models? The Q formers are tiny, tiny. Tiny as in you can train it on your own machine, which is remarkable, isn't it? Right. You can train it on very simple hardware. I believe they mentioned the sizes somewhere. It is not even a gig, if I'm right. It is tiny. Somewhere they mentioned. Yeah, they're very tiny. Then let's look at the output. This is where you'll be surprised, actually, how well it does. Look at this. Explain the advantages of this product. What is this product? A car, a picture of a car. And the input is like, now it is behaving like a, literally like ChatGPT these days, isn't it? You give it a prompt and you say, explain the advantages of this product. You're not telling what it is. Would you have expected this response? The Audi e-tron Quattro concept is a plug-in hybrid electric sports car that has a range of 310 miles and can accelerate from 0 to 60 in just 4 seconds. I couldn't have said that. I had no idea what this car is. Guys, I don't know. Does this look impressive? Right? Let's look at the second one in the middle, first row middle. Tell me something about the history of this place. The Great Wall of China was built by Emperor Blah to protect the emperor's capital from invading. So how did this happen? See, what is happening is that you know that the answer is being produced by the LLM, but the image grounded text produces just the right triggers for it to know.
LLM has the context of part node, everything. Right?
Exactly. Exactly. That is right. So instead of a prompt, we're giving it an image grounded prompt vector. Right? And that is the beauty of this. Let's look at the write down the facts that you know about this flower. And it will tell you it's an orchid. Right? That grows. But here's the best part. Look at this guy. The second row, you see that this is an unusual image, isn't it? You ask it, is this photo unusual? And it says, yes, it's a house that looks like it's upside down. I don't know, but this is quite impressive, isn't it? And you can download and run this model. How could someone get out of the house? And it even tells you. It has a slide on the side of the house. Knows that the doors are no use.
The puppy, if they want to know anything about the home, they will know.
They'll know. Okay. And look at the middle picture. It's funny. What are shown in the photo? A man and a chicken. What does the man feel and why? He's scared of the chicken because it is flying at him. Right? But the examples get even better. What are the ingredients I need to make this? Do you see how wonderfully image grounded the input is, right? So you use the full power of an image encoder, the full power of a LLM, and just put strategically the perfect bridge Q former in between.
How did that know this all, because some of that is visible. Like
Yeah, it doesn't.
How did that know oil, salt?
Because it's a LLM. See, it's probabilistic association, right? Yeah. Once you know pizza, you can't make a pizza without some salt in it. Yeah. So, and what is the first step? And that of course is coming from the inner knowledge of the LLM. Right. Now, look at this. This is, of course, the iconic Singapore picture. And this one is rather sad. What happens at the end of this movie? So giving it a picture, but it says the Titanic sank, right? So it just sounds sad. Did blah character survive? No, he drowned. What is in this photo? A pizza that looks like a cat. What is the nose made up of? And it can tell you. Just shows you how well it understands images, isn't it? So this, folks, today it was a day for introducing you to visual language understanding. Do you feel now that the machines are understanding the images? Vision. To it, vision is a language. Like it's deciphering, it's understanding the picture, not just blindly, let's say, converting a picture to black and white or filling up the spots or doing something like that. It has a pretty good understanding of the images. Yeah, go ahead.
So in the phone, if I download it, if I go somewhere, I take it through my camera, it immediately says that what is the image? Right?
Yeah.
So is it maybe the different model?
Yeah.
Okay, let me just say that I am privy to a lot of inside info. So I'm a little hesitant to say, but the simple answer is, yes, this is what is happening. But beyond elaborating it.
So, I mean, obviously, when the pictures, when the pictures becoming complex, right? So when it goes to machines, designs, that kind of stuff, still gives the outcome.
This particular model won't. These are still baby steps. Huh?
Yeah.
We are in the evolutionary step. This itself is amazing, isn't it?
Yeah, it is.
One basic rule is never use something bigger than you need because there's a computational cost. So start small, see which one works for you and stick with that. Right? So for example, you can get at the end of the day, when you have to fine tune the model on your data, the bigger the model you fine tune, the more the overall cost. Right? Yeah. So you have to ask, what is the smallest model I can fine tune and get my job done? That's a question.
That's like now BLIP-2 is like all that I need.
Yes.
BLIP is expensive, right?
BLIP-2 is much cheaper to do. And guys, if you think this was fun, remember this is day one of your multimodal learning in visual language, VLU journey.
Considering that people will have many things to process, BLIP-2 is the direction. Okay, maybe they're better.
Oh, we'll learn a lot of things.
The latency becomes very important, right?
Yes. Oh, but these machines run blazing fast. They run very fast. Most of the compute time is just the LLM itself, which is sort of like a fixed cost. You have to pay the LLM. You have to pay the piper. That's there. But the image encoding in the Q format is blazing fast. Oh, yeah. BLIP-2 are used quite a bit. Oh, yeah. BLIP-2 superseded BLIP. The only reason I went through BLIP is so that you could understand the architecture. You notice that I zipped through BLIP-2. The reason is the architecture is exactly the same. Right. Only thing you did is the first and last pillars you changed. And minor changes. You threw in learnable vectors, learnable ways, and so forth. But basically, it's the same thing. So it was important to understand BLIP to understand BLIP-2. I've seen many people jump into BLIP-2 and say, okay, what is going on? No, you have to know BLIP to understand this. But yeah, today you use BLIP-2. And more things, there are more things you'll come to. Right? This is at the beginning. There are situations where you would use BLIP-2. There are situations you would use other models. I'll introduce you through this course to many, many things. The only request I have is two things, guys. The project that I gave you, do it. What's the project? Does anybody remember?
That's the Hugging Face, WIP image.
Notebook LM. The capstone project is to do the notebook LM on your own, right? And your homework is go to Hugging Face, get these models and use these models. Please do that. Guys, at the end of it, if you don't practice, it will all wash out. You won't get caught. It is very empowering when your code actually works and you see it working, right? You'll be filled with ideas on how to use it in my workplace. Right? But that moment comes when you actually do it yourself. Let's read the next one. Write a romantic message that goes along with this photo. Guys, can you imagine that machines can do it today? And it comes up like this. Rather cheesy writing, but love is like a sunset. It's hard to see it coming. But when it does, it's so beautiful. Right? Next is a picture. And again, you can see the power of AI as it has accumulated, visual language understanding. Write a conversation between the two animals. And it says, cat, hey dog, can I ride on your back? Dog says, sure, why not? Cat, I'm tired of walking in the snow. You can imagine all of these are evidence of visual language understanding, right? Understanding what is in the image. That's all I wanted to say. And that is the gist of this paper. Right? There are benchmarks, all of it proving that it has achieved state-of-the-art and so forth. Right? So here's some funny words. Write a famous quote said by this person. Right? So it comes up with that. Can I wear this for my trip to Canada in December? You realize that you're not asking it to describe the image. Right? It has a sense that you can't be in the winter. It's a nice shirt and short, but it's a little too casual for a trip to Canada. But it did not factor in the weather. It was wrong, actually. So this also is wrong. This code doesn't belong to Einstein. Then please write the specifics of this product. Not quite right. So there are some incorrect examples it mentions. Then that's it. That is it. So guys, I obviously did the second paper, BLIP-2, a bit fast because I know that many of you have to leave. But it's straightforward paper, just a minor extension of BLIP-2. But with its main contribution is the improved efficiency. You have a much smaller model, right? Giving you the results. Please read BLIP-2. So today we covered how many papers? 3. BLIP-2. Please, this week review it. But try the code out in Hugging Face. Right? Play with it. And think about how you will create your own imitation or a better version, your own personalized version of Notebook LM. Right? Look at each piece of the puzzle and do that. Right? And from next week, start making small demos of your progress. Okay, guys. So with that, I'll end today.